linear differential equation of second order with variable coefficients. We have already looked at some of the methods. Let's look at the next method, that is method of variation of parameters. Let's say the equation that we have to solve is d2y by dx square plus p dy by dx plus qy is equal to r, right? Now here what we'll do is, let's say this is the equation 1. This is what we have to solve. Now what we'll do is we will say let r equal to 0. So in which case what happens? We end up with the equation d2y by dx square plus p dy by dx plus qy is equal to 0. Let us say this is equation 2, right? Now for this equation, the solution using any method would be what? Would be y is equal to c1u plus c2v, right? Where u and v are functions of x and c1 and c2 are arbitrary constants, right? Now what we are going to do is we are going to replace the c1 and c2 with something else which will lead us to the solution to the first equation, right? So substitute c1 and c2 with functions of x such that we have complete solution for 1, that is where right hand side is r. Okay, so let's begin. Let's see how it works out. So let r equal to 0, we got a homogeneous equation. Then y is equal to c1u plus c2u. Now because r is equal to 0, this is the complete solution of the second equation, right? Okay, now let y be equal to, instead of c1 c2 we are going to put it as a and b. So au plus b v, sorry, this should be v, c1 cu c1u plus c2v. Okay, here a and b are going to be functions of x such that au plus bv is the complete solution of equation 1, right? So now here we have two variables, right? We have two variables, which means we require two equations to figure out a and b. Now y is equal to au plus bv, right? So let's differentiate this dy instead of writing, because as you will notice as we go along, we'll end up writing a lot of dy by dx and all that. So we will use a different notation, and we will use this notation is equal to a as it is, u first derivative of u plus derivative of a times u plus b first derivative v plus b first derivative of v. Now here we don't want to end up with derivatives of a and b, right? Here we have a and b. Here also we want a and b only, but not the first derivatives of a and b. So first derivatives of a and b are there in these two terms. So what we'll do is we'll say let a1u plus b1v equal to 0 to get rid of first derivatives, first or higher derivatives of a and b, right? y1 is equal to a u1 plus b v1. Now let's differentiate this again. So we get y2 is equal to a u2 plus a1 u1 plus b1 v1 plus b v2, right? So what do we have? We have y. We started off with y. We differentiated once to get the first derivative, then we differentiated again to get the second derivative. Now let's put this in equation 1. So our equation 1 becomes, remember our equation is d2y by dx square plus p dy by dx plus qy is equal to r. Now d2y by dx is this one, au2 plus a1 u1 plus b1 v1 plus bv2, that is this. Then we have plus p times au1 plus bv1, this is our first derivative, and then q times y, and y is au plus bv is equal to r. Now let's open up the brackets and also do some grouping of a, b and so on. So a would be u2 plus a is here, a is here. So u2 plus pu1 plus qu plus, now b is this and b is this and b is this. So this would be bv2 plus pv1 plus qv. Then what else do we have? We have, now this is gone, we are left with only these two. So a1 u1 plus b1 v1 is equal to r. Now just before we said u and v are solutions of the homogeneous equation, yes, where r equal to 0. So which means u2 plus pu1 plus qu is equal to 0. Similarly, v2 plus pv1 plus qv is equal to 0. So if these two are 0, what we are left with is only this. So which means we are left with a1 u1 plus b1 v1 is equal to r. Okay. And we already have a1u plus b1v is equal to 0. Yes. This equation we already have. That is there here. You see. a1u plus b1v is equal to 0. And this one we just now arrived at. Right. So which means now we have these two simultaneous linear equations. Now what we'll do is we'll use the matrix method, right, to figure out. And we know that for a solution to exist, the determinant has to be not 0, right? So solution exists if the determinant is not equal to 0. So let's say W is the determinant, U, V, U1, V1 should not be equal to 0. Why it should not be equal to 0? Because as you will see later on, this W will come in the denominator and the denominator cannot be 0. And another thing is here, this is called Wronskian of the function u and v. Okay. Now we also know that the determinant will not be 0 if u and v are linearly independent. What does that mean? That means one function is not a multiple of another for any k, because then by the properties of determinant you will end up with 0. Okay, so now let's solve these two equations. We have arrived at the determinant, so let me write that equation again. A1u plus b1v is equal to 0. A1u1 plus b1v1 is equal to r. Now here A1 b1 would be equal to 1 by the determinant, that is w, times uv u1 v1, the inverse of it, times 0 r. Remember, u1 v1 is the first derivatives. Okay, so now 1 by w times, now the inverse of this would be what? It would be v1, exchange the values of the principal diagonal u, and then just change the signs of the alternate diagonal, minus u1 minus v times 0 r. And now 1 by w, multiply this. So when you multiply, what happens? v1 0 is 0 minus vr. Now minus u1 0 is 0 ur, right? So which means a1 and b1 are this, or in other words, a1 is equal to 1 by w times minus vr, or we can just say minus vr by w. Now remember, here w is going to be the determinant, right? So uv u1 v1, which is equal to uv1 minus vu1, and this should not be equal to 0. Now similarly, b1 is equal to 1 by w times ur, or ur divided by w. Yes, but remember, a1 and b1 are the first derivatives. What we want is a and b. So a would be equal to what? It would be the integral of a1 plus c1, which would be some function of x plus c1. Similarly, b would be equal to the integral of b1, that is the first derivative of b, plus c2, which would be some function of x plus c2. Yes, now remember, we started off with complementary function of y is equal to c1u plus c2v for RHS equal to 0. We assumed y is equal to au plus bv, right? Remember this? So now let's do the necessary substitutions. Y is equal to a times u. So a would be what? A would be f of x plus c1 times u, plus b is again some function of x plus c2v. So which means we can write this as c1u plus c2v plus u f of x plus vg of x, right? So you get this complementary function plus the additional part of the solution. Now here remember, c1 and c2 are the coefficients and can also be called parameters and are constants. Using this, we have arrived at A and B, which are functions of x. Therefore, the name variation of parameters. Yes. So let's do one problem to understand how this works out, right? So let's say the problem is d2y by dx square minus y is equal to 2 by 1 plus e to the power of x. Okay, now remember this can be written as d square minus 1 times y is equal to 2 by 1 plus e to the power of x. Now, depending on the kind of problem we have, we may use different methods to arrive at the complementary functions, right? So here, because of this, we are using a particular method. So here, this would be, this can be solved using, for the complementary function, auxiliary equation. That would be m square minus 1 equal to 0, which implies m is equal to plus or minus 1, right? So which means the complementary function is what? Y is equal to c1 e to the power of x plus c2 e to the power of minus 6, purely based on this, right? Now, let's say the complete solution. This is the complete solution when r is equal to 0, right? So let us say the complete solution for the given equation where r is not equal to 0. Complete solution is y is equal to ae x plus b e minus x, right? As part of the derivation, we looked at v is equal to c1u plus c2v. So here u would be equal to e to the power of x and v is equal to e to the power of minus x. Remember, we also require u1, v1. Remember? So u1, which is the first derivative, is e to the power of x. And v1, which is the first derivative of v, is minus e to the power of minus x. Right? Now we have to calculate the determinant. Okay, u1 v1. Okay, let's substitute. U is e to the power of x, v is e to the power of minus x. u1 is e to the power of x, v1 is minus e to the power of minus x. Okay, e to the power of x times minus e to the power of minus x minus e to the power of x times e to the power of minus x. So this becomes, these two get cancelled, we are left with 1. So minus 1 minus, again these two get cancelled, minus 1. So which is equal to minus. Okay, so that means since it is not 0, that means solution exists. Okay, now A1, remember A1 is going to be minus VR by W. Now V is what? V is e to the power of x, no, e to the power of minus x, minus e to the power of minus x times r. Now r is what? That is part of the equation, right hand side, 2 by 1 plus e to the power of x. 2 by 1 plus e to the power of x. Now what about w? W is minus 2. So 2 and 2 get cancelled, minus minus gets cancelled, and we are left with e to the power of minus x by 1 plus e to the power of x. That is A1. B1 is equal to UR by W. Now U is e to the power of x, W is minus 2 times R, that is 2 by 1 plus e to the power of x. 2 get cancelled, we can take the minus 2, the numerator, 1 plus e to the power of x. Right? Now we have got a1 and b1. Remember, first derivatives of a and b. What we want is a and b. So let's figure out a. So a would be integral of a1, right, plus c1, which is equal to integral of e to the power of minus x by 1 plus e to the power of x dx plus c1. Now for this we have to do the substitution method. So let z be equal to e to the power of x. Let's differentiate dz by dx is equal to e to the power of x itself. This e to the power of x is nothing but z is itself. So dz by z is equal to dx. Separating the variables. Okay. So now if we do the substitution, what do we get? We get a is equal to integral of e to the power of minus x dx. This minus e to the power of minus x can be taken down. So it becomes e to the power of x. E to the power of x is z, right? Then instead of dx, we have to write dz by z. So dz by z. This z is for this e to the power of minus x, and this z is for this dx, times 1 plus e to the power of x is z, right? So this becomes integral of dz by z square 1 plus z. Okay, now what do we do in this case? The best way is to actually split it into partial fractions, right? So which means we have to apply partial fractions concept. So 1 by z square times 1 plus z can be written as a by z square plus b by z plus c by 1 plus z. Okay, this can be written as a times 1 plus z plus b times z times 1 plus z plus c z square, right? And on this side 1. Here in the denominator you will end up with z square times 1 plus z. Here also you have z square times 1 plus z. They both will cancel out. Okay, here let z be equal to minus 1. If you put it as minus 1, what happens? This becomes 0. This becomes 0. Right? And here if you put minus 1 square is 1. So c becomes equal to 1. So c is equal to 1. Now, let's say z is equal to 0. So here if you put 0, what happens? A remains. Here if you put 0, the whole thing disappears, 0. Here also it becomes 0. So a is equal to 1. Right? Okay. Now in this case what happens? There is no other thing that we can do by which something can disappear. Okay, so now let's look at the z square aspect. So z square is what? Cz square, and here bz times z. So bz square plus cz square, right? So z square b plus c is equal to what? 0. So this gets cancelled out. B plus c equal to 0, or b is equal to minus c, which means b is equal to minus 1. So which means that this integral can be split into 3 parts. 1 by z square, a is 1, remember, b is minus 1, b is minus 1, so minus 1 by z plus c is 1, so 1 by 1 plus z dz. Yes, of course, plus c1 plus c1. So here this is separate. Now let's differentiate this. So one by one we can do it. This becomes minus 2 plus 1. So this becomes minus 1 by z minus this is log z plus this is log of 1 plus z plus c1. Again minus 1 by z plus log of, remember this is 1 plus z and this is minus log of z. So minus becomes division plus c1. Now we can substitute back the value of z. So we have minus 1 by e to the power of x plus log of 1 plus e to the power of x by e to the power of x plus c1. Remember this is a. Similarly, we have to figure out b. So b is equal to integral of b1, which is equal to integral of ur by w. And remember, we will have another constant of integration. Okay, now this, let's do the substitutions of ur and w. So integral of u is e to the power of x divided by w is minus 2 times this is 2 by 1 plus x, no not x, e to the power of x dx plus c2. Here 2 cancels out. We are left with e to the power of x dx by 1 plus e to the power of x plus c2. Okay, now again we have to do substitution. Let z be equal to e to the power of x. So this becomes dz by dx is equal to e to the power of x, which is nothing but z. So dz by z is equal to dx. So this can be written as z dx is dz by z times 1 plus z plus c2, right? Integral. Now z and z cancel out and we are left with integral of dz by 1 plus z plus c2. And this is straightforward log of 1 plus z plus c2, which means this is log of, by the way, I missed this minus sign, right? So let's bring this minus sign. That is why it is better to bring the minus sign out as early as possible, right? Then you tend not to miss it. So minus log of 1 plus e to the power of x plus c2. This is okay. Now remember, we started off with by assuming a is equal to au, y is equal to au plus bv. So now let's do the substitution. U is e to the power of x. Now a is, if we go back, a is minus 1 by, or what we can do is we can say minus e to the power of minus x. Minus e to the power of minus x plus log of 1 plus e to the power of x by e to the power of x plus c1 plus e to the power of minus x times c2 minus log of 1 plus e to the power of x. Okay, let's do a little bit of simplification. What we don't want to start with the minus itself, so let's take c1 first. So c1 e to the power of x, then minus here e to the power of x times e to the power of minus x, numerator denominator. So it becomes 1 plus e to the power of x. Manipulate this and you will end up with 1 plus e to the power of minus x, right? Sorry, this, manipulate this and you will end up with this. uh, and then we have plus C2 e to the power of minus x minus e to the power of minus x times log of 1 plus e to the power of x. Okay, let me just very briefly do this. 1 plus e to the power of x by e to the power of x log, right? So here log of this can be written as 1 by e to the power of x plus 1. Yes. Now this can be written as e to the power of minus x. Only thing is while writing, I've changed the order. Okay, so we have this, and this is the complete solution. If you want, we can just rearrange it so that a particular point becomes very apparent. C1 ex plus C2 e minus x plus ex log 1 plus e to the power of minus x plus, no, not plus, minus e to the power of minus x log of 1 plus e to the power of x minus 1. Remember, we started off with this using the auxiliary equation, and this is what we have arrived at, the additional part of the solution. And it may be lengthy, but it is pretty straightforward. Just one or two steps of calculus. Okay, so that is variation of parameters method for solving linear differential equations of second order with variable coefficients. That's it for today. Bye for now.